Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at L'Hopital's rule, review, and preview with TI Technology. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make those tough to teach, tough to learn concepts accessible to all my students. I'm really excited to introduce our two panelists tonight. With us we have Vicki Carter and Steve Kokoska. Vicki has been teaching high school math for 40 years and currently serves as the math department chairperson at West Florence High School. She is co-chair of the AP Calculus Development Committee and serves as a question leader at the AP Calculus reading. Vicki has served on TI-Nspire authoring teams and has presented at many international, national, and regional conferences in the area of technology, calculus, and statistics. Thanks for being with us, Vicki.
I'm enjoying getting to meet everybody and talk with you tonight.
And Steve received his undergraduate degree from Boston College and his master's and PhD from the University of New Hampshire. Steve just completed his term as chief reader for the AP Calculus reading. He has written several graphing calculator manuals to accompany statistics and pre-calculus, and has given numerous presentations on graphing calculators and AP Calculus at College Board workshops, the T-Cubed International Conference, AP National Conference, NCTM, and to area high school students and teachers. Thanks for being with us, Steve.
Thank you, Michael. It's wonderful to lead off TI's fall webinar as we all sort of think about back to school.
Absolutely. It's coming up quickly. If you have any questions during the webinar for Vicki or Steve, please feel free to use the chat window or that Q&A window on the right side of your screen. If you're new to this WebEx format and the online webinars, we'll begin sharing our screen in a few minutes, and once we do that, those windows to your right will automatically be replaced with a green floating toolbar at the very top, and you can find that chat window and also the Q&A window at the very top. The Q&A window is underneath, there'll be like an eject looking button, and it's hidden under there. But again, once we go and share our desktop, there'll be a green floating toolbar that you can access those windows at the very top. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate in the WebEx menu, choose Audio Broadcast, and then click Join. At this point, Steve is going to discuss our agenda.
Thanks, Michael. We've already did a little bit with welcome and introductions. We'll start off with a little bit about L'Hopital's rule. Vicki is going to do a very cool technology activity on the TI-Nspire. She'll pass it back over to me, and I'll talk a little bit about L'Hopital's rule analytically, a little bit about motivation, and I'll do several examples, and we'll sprinkle in some more technology in there. Towards the end, we'll mention some other indeterminate forms, and we'll take a look at one free response question that I made up, and we'll think about how this might be scored. We can only anticipate how this will be scored if there is a L'Hopital question on next year's exam, but we'll give it a shot. And towards the end, we'll also mention some other online resources that might help you with this topic. And Michael will talk more about the webinar giveaway, which I guess is a complimentary registration for the T-Cubed International Conference coming up in the spring.
Thanks so much, Steve. And Vicki is going to discuss our expected outcomes.
But tonight we hope that you will be able to see how the basic rules for evaluating indeterminate forms are developed and how we can use L'Hopital's rule to evaluate those limits. We will, as Steve just said, explore an AP-type question and not only how the student should answer it, but also sort of a sample scoring that might possibly be used. And, well, that's kind of what the third bullet is about, how the scoring might go with a L'Hopital's rule question on the AB exam.
Thanks so much, Vicki. And Vicki is going to begin sharing her desktop. And before Steve gets started, again, I just want to mention that as Vicki is sharing her desktop, those windows on the right-hand side are now replaced with that green floating toolbar at the top of your screen. And if you want to, you can bring up the chat window or that Q&A window and have those open during the webinar as Vicki and Steve are presenting. And if you have questions, please feel free to ask those during the webinar. I know we'll try and get some of those questions answered live. Steve, it's all yours.
Okay, thank you very much, Michael. So here's a little bit more about some of the topics we'll cover tonight. I am going to mention very briefly the AP Calculus curriculum framework and how L'Hopital's rule fits into that. We'll talk about background and motivation for your students, both using technology and some analytical examples. And then we'll do several examples on how we would solve those limit problems using L'Hopital's rule. And then again, towards the end, we'd like to take a look at a free response question, what a free response, part of a free response question might look like involving L'Hopital's rule, and how that might be scored so that that will help you prepare your students in the event we see a problem like this next year. So in the curriculum framework, the only thing that really changed for us in AP Calculus are the following. In Calculus AB, the only thing that was added was L'Hopital's rule. And I really have to add a little bit more in here because I've received this question several times. This only involves the indeterminate forms of 0 over 0 and infinity over infinity. You and I know that there are other indeterminate forms, and you probably will teach those in your class, but those won't be tested on the exam. In Calculus BC, just for completeness here, there are 3 topics that are added: the limit comparison test, absolute and conditional convergence, which at least in my mind really isn't new. We've actually asked questions involving these ideas before, but not necessarily using that terminology. And I know we've asked questions before involving an alternating series error bound, but never really used that terminology. So you've probably been teaching, if you've been teaching BC Calculus, you've probably been teaching at least 2 out of those 3 topics. So not much has changed for us. And I do want to remind you that no topics have been deleted from our existing AP Calculus program or syllabus. So I'm going to hand it over to Vicki now, and she's going to try a little bit with technology, and I think there's very cool technology activity.
So on Math-Inspired on the education.ti.com website, if you go to Inspired Activities and go to Calculus and look under the title of Limits, you will find this particular activity, a tale of 2 lines. So this is sort of the screenshot you would see from the website, but I'm going to go to it now. And this is the first page. It's actually only a 2-page document, but this gives a little bit of direction here that we're going to see 2 graphs that intersect the x-axis at a common point at x equals a, and we want to compare the ratios of the y values at other points to the ratio of the slopes. There is a very nice teacher document that will guide you through this, as well as a student document, and I'm talking about something that you could copy, a paper document that will guide the students through this activity that works very well. We're just going to talk about it quickly here so that you'll get an idea of what the document does. So I'll go to page 1.2, and this is where all the activity is. And what you will notice is that it appears that we have 2 linear equations. One of them is red, and it has a positive slope, and one of them is green, and it has a negative slope. The scales on the x and y axis are equivalent, although they aren't given, but what the students are actually asked to do is find the slope of each of these 2 graphs. So the slope of the red graph is 1, and the slope of the green graph is -1/2. So if we were to do the ratio of the red slope to the green slope, we would have -2. The students are then asked to find some other points that would be located on either the red line or the green line, and then find the ratio of the y values there at the corresponding x, and the students would then determine that they get this common ratio of -2. Then at this point, there's a few questions that sort of ask them about, well, what would you think the limit would be as x approaches a, which is this point of intersection of f of x over g of x? And so hopefully the students could reason that that limit would be -2. And then the students are asked to use the zooming tool, which is this slider bar here, and we want to zoom. And let's see what happens. So as we zoom, you will notice that what appeared to be lines now turns into a parabola and a sine function, or at least a sinusoid, a trig function, sine or cosine. And we find out that if we, basically you're looking at this idea that the graphs are locally linear at x equals a. And so what we were really looking at were the slopes, the ratio of the slopes of those linear tangent, kind of thinking about tangent lines. And so then the students are guided into thinking about, well, the limit as x approaches a of f of x over g of x would be the same as the limit as x approaches a of f prime of x over g prime of x. And then they're sort of guided into, wow, this is a statement of L'Hopital's rule. It's a very, very nice activity that gives the students a graphical sort of interpretation of L'Hopital's rule before you actually go into examples. All right, Steve, I'm going to pass it back to you.
Okay. So that activity, that technology activity, at least in my mind, presents some not only motivation for L'Hopital's rule, but also some justification as to why that works. So if you sort of keep that activity in the back of your mind, I'm actually going to come back to that when I finally state this rule. So let me talk a little bit about what I think of as the analytical setting and why we might need this kind of a rule. So bear with me a little bit. I might take a look at this function, capital F of x in my class, log of x divided by x minus 1. And I might think a little bit about the domain of this function first. It's got a natural log in the numerator, so I know x has to be greater than 0. It's got an x minus 1 in the denominator. So certainly capital F is not defined at 1. And even though it's not defined there, I might like to know what's the behavior of this function, capital F, like near 1. So in order to answer that question, I might want to consider this limit. The limit as x goes to 1 of log x divided by x minus 1. So this is the way that I attack limits, at least in my class. I always look for the easiest thing first. And one of the easiest ways to evaluate limits is through direct substitution. Now, I probably put too many steps in this first slide here, but there's some properties of limits going on where the limit of a quotient is the quotient of the limits, but I've eventually done direct substitution. And when I do that, I get 0 over 0. And at least I tell my students, whenever you see 0 over 0 through direct substitution, that's a sign. That's a signal that you need to do something else. And so at least at this point in the class, I'm sort of stuck a little bit. I don't know what to do with this. I don't know how to evaluate this limit. I don't know how to answer that question. What's the behavior of this function like near 1?
And Steve, I tell my students the same thing in high school, that when they see a limit through direct substitution or the use of the limit laws and get to 0 over 0, there's more to come. We've got to do some more work.
All right, let's take a look at the next page. So this idea here, this direct substitution, leads us to this definition of this kind of a limit. So the limit as x goes to a of f divided by g is an indeterminate form of type 0 over 0 if both f and g are going to 0. So that is a quotient. I've been thinking a lot lately about common errors on the AP Calculus exam, and just common errors that my students make. And I think there's one actually here in this definition. That is, I think many of my students, when they see this, think that that must be a rational function, the quotient of two polynomials, and that's definitely not true. This is just the quotient of two functions. Well, the next thing I would talk about is, well, wait a minute, if we see this kind of indeterminate form of 0 over 0, let's not forget some other solution techniques that we have. We might be able to solve one of these limit problems without anything additional. And one of the ways, I think, is with clever algebra. You've probably already done this earlier in your class. In this particular problem that I've shown you, we can solve this limit by factoring both the numerator and the denominator and doing a little bit of canceling. One of the things that I tell my students, I don't have the pointer in front of me here, but one of the things I tell my students is that function on the right and the one that I began with on the left are exactly the same everywhere except that one. And so if I want to know what the left-hand one is doing near 1, I can ask, what's the right-hand one doing near 1? And in order to find out what that right-hand function is doing near 1, in order to evaluate that limit, well, darn it, that's just direct substitution, and that gives me a 1/2. Now, one of the other solution techniques we have is what I would call a geometric argument. I don't think we do too many of these in class, but I think we often gloss over one, at least when we derive, I think it's the derivative of the sign, and so this one shows up as a geometric argument. But we still need another technique. We still need another technique in order to solve that problem that we started out with. Well, before I get there, there's another situation, there's another sort of a limit, and it's this one. Consider the limit as x goes to infinity of the log x divided by x minus 1. As x increases without bound here, the log of x increases without bound, it goes to infinity, and so does the denominator. And so the question is, as both of these functions are increasing without bound, is one of them sort of winning out? If the numerator is increasing faster, that's driving the whole equation, the whole fraction to infinity. If the denominator is increasing without bound faster than the numerator, then that drives the whole fraction to 0. Or one way that I think about this is there some sort of a compromise? Is this fraction, is this ratio sort of zeroing in on some finite number? And so as before, a limit of this form, where f and g are both going to infinity or minus infinity, that's called an indeterminate form of, darn it, infinity divided by infinity. And I remind you that that limit may or may not exist. So we have some other solution techniques to handle this one too. Remember, if we have the quotient of two polynomials, and we want to know what happens as x goes to infinity, our standard way to solve this is to divide both the numerator and the denominator by the highest power of x in the denominator. And so there's an example of that solution technique. We know that as x increases without bound, a constant divided by x to the n goes to 0. And so we can eventually evaluate that, not quite by direct substitution, but that problem, that limit simplifies or evaluates to 1/2. All right, so we've got these two sorts of indeterminate forms. Now we need a way to solve them. And on the next slide, I think I've given you L'Hopital's rule. If we have an indeterminate form of either 0 over 0 or infinity over infinity, then L'Hopital's rule says the original limit is equal to the limit as x goes to a of f prime divided by g prime. I'm going to pause there for a second and mention another common error, a common error we see on the exam and in my class, is that students get this confused and think, oh, well, I've got a quotient, I've got to use the quotient rule, and of course that's not true. We take the derivative of the numerator separately, we take the derivative of the denominator separately.
So this is a good time to, when you present L'Hopital's rule, and if you've done the exploration, a tale of two lines, that you can try to emphasize the fact that it's not a quotient rule, because you can remind the students that we looked at the ratios of the slopes of that red line and that green line when we explored that TI-Nspire document. So it's kind of good to give them something to kind of go back and look at and think about that they've done graphically or, you know, with their calculator or something like that. All right, Steve.
Okay, perfect. A couple of notes on this next page, and then we'll do a couple of examples. I want to remind you that it is important to verify the conditions before we use L'Hopital's rule. I'd like to suggest that you emphasize that to your students when they take the AP exam, that they should demonstrate that the numerator and the denominator are both going to 0 or plus or minus infinity. And I want to remind you, too, that L'Hopital's rule is valid for one-sided limits and for limits at positive or negative infinity. So as x goes to a from the right, for example, or as x goes to infinity or minus infinity. And this third bulleted note on this page is a special case. I didn't want to put the word proof in there because I know that's a dirty word, but I wanted to take a look at this special case. Let's suppose that f of a and g of a is equal to 0. This kind of gets us back to that tale of two lines. And let's suppose that f prime and g prime are continuous and g prime of a is not equal to 0. What I'm going to do is to sort of work backwards. I'm going to start at the conclusion, and I'm going to try to end up here at the very beginning of L'Hopital's rule. So let's take a look at the limit as x goes to a of f prime divided by g prime. Well, if f prime and g prime are continuous, then that means I can just use direct substitution and evaluate that limit. And so that's f prime of a divided by g prime of a. In the next step below that, I'm going to use what I call the alternate definition of the derivative in both the numerator and the denominator. And in the next step to the right, I'm going to use a property of limits. Again, kind of working backwards. The limit of a quotient is the quotient of the limits. And then working down, I'm going to cancel out the x minus a. And then finally, in that last step, I assume that f of a and g of a were equal to 0. And son of a gun, that's L'Hopital's rule in this very special case. That's kind of cool, and I think your students can understand that. There's nothing too deep there. They've got the definition of the derivative. I think that's something that they can see. And now what I'm going to try to do is to illustrate this idea, this special case, graphically. So try the next page. There we go. So here's a graphical illustration, I hope, of what I just did. There's a graph of f and g. They both pass through the x-axis at a. And on the right-hand side, what I've done is I've taken a look at a linear approximation. I've sort of zoomed in. So when I do that, f of x is approximately equal to m1, the slope, times x minus a. And g of x is approximately m2 times x minus a. But wait a minute. I can cancel out those x minus a, and that's just m1 divided by m2. And so that's a sort of a geometric illustration, a graphical illustration of what we just took a look at on the previous page. It's some graphical justification for why L'Hopital's rule works, why we can take a look at the ratio of the slopes. And I think that's kind of cool, and it kind of ties together this activity that Vicki took a look at the very beginning, the tale of the two lines. All right, well, let's try a couple of examples, Vicki, if that's okay with you.
Sounds good.
All right, so here's the first one. Let's go back to this one. Let's take a look at the limit as x goes to 1 of the log of x divided by x minus 1. I'll just remind you once again that if I try direct substitution, I get 0 over 0, and that's a signal that I need to do something. I don't see any algebraic trick here, clever algebra, and I don't have a geometric argument, so that means I'm going to use L'Hopital's rule. So in the next step, I'm going to take the derivative of the numerator divided by the derivative of the denominator, pretty straightforward. In the next step, I've got a 1 over x divided by 1. I'm going to pause here just for a second and remind you that once we take the derivative in the numerator and the denominator, you should remind your students to simplify. So I did that in the next step, and son of a gun, when I reach that, direct substitution works, and that limit is equal to 1. So that's a nice first example. Let's try the next one, and maybe we'll sprinkle in some technology here. This is kind of a neat example because we frequently talk about exponential functions versus power functions, and which of these functions grow faster than the other one. So as x goes to infinity, both the numerator and the denominator here are both increasing without bound. So the question is, again, is the numerator increasing faster than the denominator? If so, driving the whole fraction off to infinity. If the denominator is increasing faster, well, then that's driving the whole fraction to 0. And then finally, is there some sort of compromise? So I checked the conditions here. Both of those, the numerator and the denominator, are going off to infinity, so I'll use L'Hopital's rule. So I'll take the derivative of the numerator and the derivative of the denominator. I get an e to the x divided by 2x. I don't see any simplification in there. And I pause for a second and recognize, oh, hey, wait a minute, the numerator is going off to infinity still, and so is the denominator. And so I can use L'Hopital's rule once again. When I do that, the derivative of the numerator is e to the x. The derivative of the denominator is 2. And now I can evaluate that limit because the numerator is increasing without bound, divided by a constant, and therefore that limit would be infinity. I also want to mention one thing here that always sort of bothers me. You'll notice that in this answer or in this problem I put equal infinity. And I know that bothers a lot of people because infinity is not a number, it's a symbol. So how can that limit be actually equal to infinity? So here's my response to that one. That's some notation. That's some symbolism that we all agree as mathematicians. We all agree that that describes the behavior of that limit. That means that that original limit is increasing without bound. It's not approaching any one specific number. So that's notation, that's common notation that we as mathematicians agree on. So, okay, I think maybe we could try a little bit with technology here. Vicki?
Okay, so let's start with the TI-Nspire. So I'll go to a document here that we have. I've already opened a new document, and I can go through that process with you too. So I would go to my home key, and I would select number 1, new document, and of course it's going to usually prompt and ask me if I want to save that one, so I'll say no. And then it will ask me which app do I want to use. So I want to use graphs, and so that's how I arrived at the screen that you saw just a second ago. So we want to graph that function, which was a quotient. When my students are using the Nspire, I encourage them to do the template either through Control Divide or the template button that I'm kind of pointing to right here so that they have a nice fraction and don't get confused about their numerator and denominator. So in the numerator, we want e to the x, and in the denominator, we want x squared. And so let's graph this. And so we have this graph, and what we really want to explore is what's happening to this graph as x approaches infinity. So I tell my students they need to do a little more than just sort of believe what they see immediately on that first graphing window that they have. So what I might do is change my x max, x min, y max, y min. One of the favorite things my students have these days with the Nspire is to actually just double click on the endpoint numbers here that they see and change those. That would be fine to have as 0 for my y min. And then if I press tab, it just goes to my x max. It sort of rotates around clockwise around through those those 4 values that you see there. So I might want a little larger value here, so let's just try something like 20. Now I do want to explore as x approaches infinity, so maybe 10 is okay to have here, and then it looks like it's not going to matter a lot about what I have as my y min, so I might put -1. And I have a nice graph here that I sort of feel okay as a confirmation about the limit that we got through L'Hopital's rule that as x approaches infinity, so does f of x. We could trace, we could do some other things there. With the TI-84, very similar. So we would take our e to the x. So I have to do second and my natural log key here. So e to the x. And then I need to go to the right because I'm in the exponent right now. And I want to divide by x squared. And let's look at that graph. And again, we see something very similar. And we could do the same thing that we did on the previous graph, which is maybe refine our window a little bit. But this similarity to what we have already seen would, again, convince us with this calculator that our work that we did through L'Hopital's rule is correct since the graph supports it. Okay, we're ready for the next example?
One more on this slide. If you hit,
all right.
I think that's
All right. Which one do you want, the Nspire or the TI-84?
No. Just let's go one more page ahead here. In the
Oh,
PDF.
one more page down. I got you. Oh, there's that graph. That's Stephen's pretty graph.
I just wanted to show that graph created with Mathematica and mention one other thing here. We did take a look at this example as x goes off to infinity, but you know, another nice limit question is the limit as x goes to 0 from the right of this quotient. I mean, I can sort of see what's going on, but you might think about how you would evaluate that limit. I can see graphically, I think, what's happening. But that's an open question. I'll leave that. We're not doing that tonight. Thanks, Vicki. Next example.
Okay, so example 3.
Okay. So let's take a look at the limit as x goes to infinity of the log x divided by the square root of x. I'm going to check to make sure that the conditions are satisfied. As x goes out to infinity, again, log x is increasing without bound, and darn it, so is the square root of x. So, okay, I have to do something here. I have infinity over infinity. I don't see any nice, clever trick here, so I'm going to use L'Hopital. So here we go. I'll take the derivative of the numerator and the derivative of the denominator, 1 over x divided by 1/2 x to the minus 1/2. And I'm going to do a little bit of extra here in the next step. What I'm going to do is rewrite that denominator, I think. Vicki?
Yes, and remember you said something a few minutes ago about you encourage your students to do algebra simplification, and so they don't need to forget that in this step.
Absolutely. Yeah, so I did a little bit of rewriting in the denominator and then a little bit of simplifying in the next step, I think. And then I can evaluate that limit as x increases without bound, the denominator is increasing without bound, the numerator is constant, and that drives that whole fraction off to 0. Fantastic. We're going to try this one with technology?
Yes.
Okay.
Okay, so I want to add a new graphing window here. So I will add a page to this document and select graphs. And this time we want a, oh, here, I'll go through the template this time. So if we, well, not that way. Oops, I need my equals back. Click too many times and that's what happens. Okay, so if I click on the math template button here, so you will see that actually the first item is the fraction. And so that's the second way that you can get your fraction template. And so we want the log of x. And we want to divide by the square root of x. All right, let's see what that looks like. So we have this. And again, we may want to adjust our windows. So instead of adjusting it the way I did a few minutes ago, let's look at a different way that we could do this. So under menu, you will see your, if you go down to the fourth one where it says window zoom, so I'll go down to the fourth one, and then I'll go to the right and see what options I have. And here you have window settings. And so essentially that would do the same thing as the, as how I did it a while ago where I clicked on the X-min, X-max, Y-min, Y-max. And so what we might want to do here is get a little more extreme with our values. So let's do something like, we'll put 0. Let's put something really large like 8,000. And if you want to force a particular X scale, and sometimes I do, I might put 1,000, so I don't have that many tick marks kind of in my way as I look at this graph. And then we noticed that, remember that when we did our L'Hopital's rule, we got a limit of 0, right?
Mm-hmm.
Okay.
Yep.
So we were trying to confirm that. So we might want to zero in on 0 a little bit more here. So let's do something like negative 1 to 1, something like that. And the scale won't matter there. So okay. And so you see here a graph that is there's some little funny stuff going on over here near 0, but let's not worry about that because we're looking at limit as x approaches infinity. You'll notice that this graph appears to be sort of decreasing, but maybe the students don't believe that it has a limit of 0 as x goes to infinity. So maybe we need to change this to a larger number. We could get really extreme. Put one more 0 in there. And sometimes it just takes a little playing to convince the students that, yes, if you let x keep getting bigger and bigger and bigger, that graph of f of x is going to get closer and closer and closer to 0. Of course, sometimes I go on to the next example, and 5 minutes later, a student raises their hand and says, hey, Ms. Carter, I'm way over here at blah, blah, blah. And, yeah, I finally believe the limit is 0. And I go, well, that's great, but you just missed the example we're talking about. But they love to explore on the calculator. All right, so Steve, we will look at your graph here. So you made a comment that logs grow slowly, and so slowly that's why we had to look at very, very large numbers of values of x, and so you have your beautiful graph there.
Yeah, a couple of things on this page. On my note there, I don't know if we would ever ask a question like this on an AP exam, but, you know, we're stressing communication and interpretation. And I think it is nice that the students can solve this limit problem and interpret this to mean that logarithms are growing slowly as x increases without bound. Because that limit is going off to 0, that means that the denominator is growing faster than the numerator. The second thing I wanted to look at is take a look at my graph. Vicki saw a little bit of this with technology. You know, if you look at that graph very quickly, it sort of appears that as x goes to 0 from the right, and it looks like that function is going off to plus infinity, increasing without bound. I'll just leave this as sort of an open question, too. That certainly isn't correct. That's an artifact of the scale here that I have for x. But that's an example of, you know, something we might call lies my calculator told me. So that's kind of a neat graph. It supports our limit, but there's also something interesting going on the left-hand side. All right, let's try example 4, Vicki.
Okay.
All right, let's get some trigonometry in here. The limit as x goes to 0, tangent of x minus x divided by x cubed. Kind of quickly, this is 0 minus 0 divided by 0. Darn it, we need to do something. So I'll take the derivative of the numerator, derivative of the denominator. I've got a secant squared minus 1 divided by 3x squared in the denominator. I think I've got to use L'Hopital's rule once more. So in the next step, I take the derivative of the numerator, derivative of the denominator. I've simplified a little bit. I had to use the chain rule up there in the numerator. And I think I can evaluate that in the next step. Oh, I'll tell you what I did in the next step. Go ahead, Vicki. This is kind of a cool problem. In this one, what I did is I split this up here. I used the property of limits. The limit of a product is the product of the limits. And I split this up into the limit as x goes to 0 of the secant squared times the limit of that quotient. And I know I have the 1/3 out in front. I know the limit as x goes to 0 of the secant squared, but son of a gun, I have to use L'Hopital once more on that fraction tangent of x divided by x. So I took one more derivative of the numerator, derivative of the denominator, and finally I think I got a limit of 1/3. That's a very neat problem. There's lots of stuff going on in there. I think 3 versions, 3 L'Hopital's rule, and some properties of limits. Let's try this one on the graphing calculator, Vicki.
Okay. And I can't see the chat window quite like you everybody else is because I'm sort of manhandling the documents here. But I did notice some little comments going across there about giving tests with a calculator part and a no calculator part. I think what I really want to say here is that I really believe students need to explore these graphs with technology as you're taking these limits initially so that they can have a good understanding of what the graph looks like and how that complements what they're doing with their L'Hopital's rule. But I probably would not give a L'Hopital's rule question on a graphing calculator active part of my test. So don't know if that'll help you any, and it might not have even been what the comments were about, but it seemed to be headed in that direction. All right, so let me get a fraction here, and we want the tangent of x minus x and over x to the 3rd power, so x cubed. And, of course, this function is not defined at 0. Sometimes it bothers students that they can't see a hole there at 0, but the graphing ability of this calculator is so fine that holes don't appear. You can sort of determine that there's also a hole there if you want to look at the graph with the trace. But what we might want to do here is sort of a zoom in thing, because when we zoom in at 0, we could use our zoom in features. We could also grab these little tick marks perhaps and zoom with this. Well, except I can't seem to grab mine at the moment. Okay, mine doesn't want to cooperate today. There we go. All right, so I could zoom in kind of like that. And notice that I have a limit here. And what was our limit? 1/3? Is that what it was?
1/3.
Yep.
Mm-hmm.
And so, I mean, I could even maybe change my scale so that it would be a little bit easier to determine. But this looks like 0.3 and a little bit more. So a little more zooming, I might be real convinced that I definitely did my limit correctly and that I believe that the limit would be 1/3 as x approaches 0.
Vicki, I'm seeing a question about presenting something with the TI-84. Do you have a second to do that?
Yep. Okay, so let's go to our y equals and okay, I need to come, hang on, let me get that one where it won't graph it when we go to the next one. Okay. All right, so we need the tangent of x minus x and divided by x raised to the 3rd power. All right, let's look at that graph.
Perfect.
All right, so here it comes. And again, we could go do some zooming here if we wanted to confirm it in the same way that we did with the TI-Nspire.
Very cool.
Hey, Vicki.
Yes.
Would you mind just flashing back to that y equals screen for a second?
Yes.
I think we had a participant that was looking for that information.
Oh. Here?
Yep, I believe so.
Okay.
Thank you.
You're welcome.
All right, let's try example 5.
All right. Here's, oh, there's
Oh,
your pretty graph with a hole in it.
Okay. And so this is an example of what might happen if you use L'Hopital without just cause. What I mean by that, of course, is without checking both the numerator and the denominator. So we take a look at this limit and we just blindly use L'Hopital without any check here. This is what happens. Take the derivative of the numerator divided by the derivative of the denominator without cosine, divided by the sine. And from here, this is the way that I might evaluate this. As x goes to pi from the left-hand side, the numerator is going to -1. And I use this sort of notation in the denominator. The denominator is going to 0 through small positives. And so that's how I would denote that in my class. And so if that's true, this whole fraction is going to -1 divided by small positives, and that's driving the whole fraction, the quotient, to -infinity. Now that's wrong. That's absolutely wrong here. On the next slide, what we should do is just evaluate this one by direct substitution right away. And the answer is 0. So that's a very nice example, I think, of what can go wrong here if students don't check to make sure that the assumptions for L'Hopital are satisfied.
And as a high school teacher, I will definitely say that once students learn L'Hopital, they think it is the dream answer to every limit problem they will ever see from there on out, and will use L'Hopitals every time. So you're really going to need to present some of these so that the students don't use L'Hopital without just cause.
All right, and kind of quickly on the next page, we just wanted to remind you about some other indeterminate forms. These are not in the curriculum framework, and these wouldn't be tested on the AP exam, but they are, at least in my opinion, kind of fun to look at. So we have an indeterminate product of f times g, where one of the functions is going to 0 and the other is going to plus or minus infinity. That's an indeterminate form of type 0 times infinity, and what is that limit? No, we don't know. We have to do something else here. And in general, we want to get it back to something that we know about, typical problem solving. We try to get that back into a form of 0 over 0 or infinity over infinity. The next indeterminate form is a difference, infinity minus infinity. It kind of seems like 0, but remember those are symbols, not numbers. So we don't know what that is. We want to get that back to something that we know about. And finally, we have 3 different types here involving an exponent. 0 to the 0, it seems like it ought to be 1, but isn't necessarily. Infinity to the 0, and 1 to the infinity, all indeterminate forms, and all need some extra work in order to get it back to something that we know how to handle. Okay, terrific. Let's take a quick look at what a free response question might look like, and I'll tell you what I think a grading scheme might look like. So this wouldn't be obviously an entire free response question, but part of one. Let's suppose we want to take a look at the limit as x goes to 0 of the arctan of the tangent inverse of x divided by e to the x minus 1. We would really like students on the exam to check the assumptions explicitly. We'd like them to show us that the numerator and the denominator separately are going to 0 in this case. And once that's true, then we'd like them to use L'Hopital's rule in the next step here and take the derivative of the numerator divided by the derivative of the denominator. Now, I'll emphasize this again, but right at that point, I see that on a student's paper. Now, again, just guessing, I would say that that's worth 1 point. That's the student has demonstrated to me that they are using L'Hopital, that actually used L'Hopital here after checking the assumptions. So one way I might word this is that they are explicitly checking these conditions in the context of using L'Hopital's rule. So on the next part of this, I think I can evaluate now by direct substitution and get a 1 divided by 1 for exactly 1 to this limit. So down at the bottom of this page on the next slide here, the points that I would see, I would argue for here are 1 point for using L'Hopital's rule, but what that really means, in my opinion, is that it's explicitly checking the conditions in the context of using L'Hopital's rule, so that if a student just wrote down that the limit of the numerator is 0 and the limit of the denominator is 0, that's not enough. And if the student just wrote down that limit expression, those equalities, that wouldn't be enough to get the first point either, at least in my opinion. And then finally, 1 point for the answer, that would be putting everything together and ending with the final numerical answer. And by the way, I can also envision this sort of a problem as a 3-point question, where the derivative of one of those expressions, the numerator and the denominator, might be a little trickier. In fact, this one might be worth 3 points because perhaps we might award 1 point for the derivative of the inverse tangent. So I can see a problem like this being worth or being scored as 2 or 3 points. Vicki, what do you think?
I think that's definitely a possibility, but I don't think we can say enough that the students really need to get into the habit of explicitly checking the conditions and stating them when they are doing practice free response questions that would be similar to something that would be on the AP exam. That is the safest bet for making sure that they get full credit.
I think this is an excellent problem, Vicki, a very simple problem that emphasizes not only communication, one of the math practices, but also notational fluency.
Absolutely.
I mean, I think you and I have seen a lot of papers where we see missing limit signs, where we see a symbol like LH. And I always tell teachers when I give workshops that, you know, we understand what MVT means and what IVT means, but LH, that's sort of in a gray area. I don't know exactly what LH means. So we really want to see some good notation in a problem like this.
Yes, so emphasize good notation throughout the course. It can never hurt. All right, so something that we thought we would share with you quickly here are some questions that have been on the BC exam that you may want to take a look at, how they were graded, and I would definitely use these with your AV students this coming year. And also there are some questions in the curriculum framework that was published in 2014, but that link will take you to just the sample questions that were in that particular document. And then, of course, our new document that is out is the AP Calculus, AB, and BC course and exam description. We fondly call it the CED, but in that you have a question, one good sample question with L'Hopital's rule, and that is the link to that particular document. And that is the document that you need to be paying a lot of attention to this year, because this framework and this course and exam description is affecting the exam that will be given in 2017.
Now, Vicki, if it's okay with you and Michael, let me answer a couple of questions that I saw screened on here. One of them is about the other indeterminate forms, and do we teach them at the college level? I can only speak for what we do here, and yes, we do teach those. I think if you look at a section in a traditional calculus book on L'Hopital's rule, you'll see those other indeterminate forms, and we don't skip them, we would teach them. The second question I wanted to answer is, you know, we get an awful lot about the spelling of L'Hopital, but if you take a look at the CED, the curriculum framework and the CED, the College Board is spelling this with the S in there, so darn it, that's the way we did it.
Okay, Michael, sending it back to you.
Thanks so much, Vicki.
You're welcome.
And before I go through my closing remarks, there was another question earlier that I thought it would be great to get your opinions on. Leanne and Michelle both had the same question, and a few other people echoed that they would love to hear your thoughts on when do you introduce this? When do you introduce L'Hopital's rule, especially depending on whether you're transcendentals or early or late?
Well, for me, Vicki, you probably have a better answer here, but for me, this comes after transcendentals. This comes after limits, of course. This comes after students have all the derivative formulas. This might be in a section on applications of derivatives.
So I'm going to tell my age and how long I've been doing this, but I was teaching AP Calculus years ago when L'Hopital's rule was in the AB curriculum, and at that time I taught it with sort of that application of graphing that would be an application of derivatives. What does a derivative tell us about the graph of a function? And I introduced L'Hopital's at that point so that it could possibly give us additional information about what we would need to know about the graph, that analysis of the graph. But that's kind of what I'm planning on doing this new year that is coming up, so that my students have an earlier introduction in my AB class to L'Hopital's rule.
Great, thanks so much. So a few things I want to share with you. Some are from our website. So I'm going to go to our website, which is education.ti.com. And it's great to see we have a lot of people on tonight that this is the first webinar and TCube professional development webinar they've ever attended. They're asking some really great questions about where to get more materials and how to get materials from tonight as well. So I'll be sending out the documents that Steve and Vicki used in a few minutes here. But in case you miss it, we are going to send you a follow-up email in a few days with a link to the recording as well as a link to the documents that were used tonight. But if you want to look through our archives and see what other webinars we've done, feel free to visit our website and slide underneath the Professional Development tab and go down to Webinars and Tutorials. There you'll find, if you go to the live webinars area, a list of all the upcoming webinars we have for the remaining summer and then this fall. Tonight is the first webinar to kick off our summer/fall webinar series. So I believe we have 16 additional webinars that will be offered almost every week between now and the end of November, early December. But you can also check out the on-demand webinars. If you click on that, any webinar we've given previously, and there's hundreds of them, have all been cataloged and archived So you can pick a specific technology that you're interested in and sort of narrow your focus that way. So whether you're focusing on the TI-84 technology or TI-Nspire technology, there's probably a webinar that can pique your interest this summer.
Michael, take one. Oh, never mind. I was going to say, just go to the activities and just show them real quick where all those calculus activities are.
Sure, good idea. So right next to that professional development tab is the activities tab. And there's a lot of different choices here, but for tonight's purposes, you're going to want to go into the math inspired. And again, lots of content here on the left-hand side. To find the activity we chose to look at tonight, we went under calculus. And then I believe applications of the derivative.
No, it's under limits, the first one.
Great, thank you.
You're welcome.
Under limits, there's
the first one.
lines. And I think the reason why I like using a lot of these math-inspired activities is I don't have a lot of time to try and find really good, rich activities. So if you click on one of these, you can watch a really quick, short video on what the activity is really about and sort of get an idea and a preview of what you're looking at before you spend a lot of time trying to decide if it's something that you want to download and use with your students in your class. But again, these are all free, able to be reproduced and used with your students at any time.
Thank you.
Thank you. I mentioned that we do have a lot of upcoming webinars, so please feel free to visit our website and view some of those upcoming webinars. They might be of a lot of interest to you. If you can't attend one of our upcoming webinars live, no big deal. Go ahead and register for it anyway, because once you register for a webinar, you'll automatically receive a follow-up email, whether you've attended or you happen to miss it. Either way, you'll get that follow-up email with a link to the recording as well as a link to the documents that were used. Also, whenever you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, and we really do appreciate your thoughts. So please feel free to share your thoughts in the post-webinar survey. As Steve mentioned earlier tonight, we're giving away a free registration for the T-Cubed International Conference, which is coming up in March this year in Chicago. Tonight's lucky winner is Vimala, I think I got it, Vimala Emmanuel. So Vimala will be in touch over the coming days over email. Congratulations. We'll definitely have more information about the T-Cubed International Conference in the coming weeks. Please feel free to keep that conversation going on any of the major social media outlets. There was a lot of great questions and a lot of great comments tonight. So please, please, please feel free to reach out and connect on social media. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents that were used tonight as well. And if you happen to miss that for any reason, again, you'll automatically receive a follow-up email within a few days. If you happen to ask a question tonight that wasn't answered for whatever reason, please feel free to reach out to us. Either give us a call or send us an email. We'd love to hear from you. All right, thanks so much, Vicki and Steve, for your time and preparation tonight. I know I learned a few things. I'm teaching AP Calculus in a few weeks here, and it's going to be great getting this kickoff webinar and learning all the things I learned tonight and using that with my students. So thanks so much for everything.
Oh, you're quite welcome.
Michael, one last thing here on the slides. My email was there. I don't know how Vicki feels about this, but certainly if anyone has a question about AP Calculus in general, and especially this webinar, they can certainly feel free to send me a question. I might not get to it right away, but I will respond. Yes,
be happy to also, although I don't think my email address is there.
No problem, guys. Well, thank you so much for everything. Again, I really appreciate it. And we really hope to see everyone back online next week. Thanks so much.
Thanks, Michael.
Good night.